Welcome. This is Year 8, Competence-Based Middle Years Program Level 3 Sciences, Session number 3. In this session, as part of Unit 1, we will go on studying uniform circular motion. In particular, we will see the linear speed of objects moving with UCM, and we will see normal acceleration. On top of that, we will analyze cogwheels. So let's proceed. Let's have a body that is moving along a circumference. At the given instant 1, it is on point 1, and we can represent v1 as the speed it has, the linear speed it has. A while later, it is at point 2, it has v2, the speed on point 2, as represented in the image. It has uniform circular motion, therefore the angular speed is constant and the rate at which the body covers the distance is constant as well. At every instant, speed equals the average speed. But as we can see, speed is changing its orientation. V1 is point upwards, whereas V2 is point slightly to the left-hand side in the image. That is why we represent that speed with its orientation with a V that has a small arrow on top. We call that representation a vector, which is the arrow. V with the small arrow on top is called velocity. It is a speed with an orientation. Those arrows are extremely important. We cannot forget them. Think of them as the heads of an individual. If you forget the arrow, it's as if you were beheading them. And it's not nice going around beheading people, is it? At each point when a body is moving, the velocity is tangent to the trajectory at every single point. As we can see in the image, on point 1, the radius is horizontal and the velocity v1 is vertical, perpendicular to the radius and tangent to the curve. In point 2, it is also perpendicular to the radius and again tangent to the trajectory. Velocity is always tangent to the trajectory in any movement. Let's illustrate what we just said with a real example. In the image, we have Valle and Sergio who are running along a circumference. There's a rope that is tied between them two, and their arms plus the rope define the diameter of the circumference. In the upper part of the image, we can see that Valle is running towards the left-hand side of the image, whereas at the bottom we can see that Sergio is running towards the right-hand side. Valle is looking in front of her and is looking towards the left of the image, whereas Sergio is looking towards the right of the image. As we walk or we run, we are always facing ahead of us. Valle's velocity, marked v2 in the image, is tangent to the trajectory towards left. Sergio's velocity at the bottom is marked v1 and it's marking towards right. So as they run along the circumference, the velocity is constantly changing. is constantly changing not in its modulus, but in its orientation. Given that there is a change in the velocity, not the modulus, but the orientation, we need an acceleration. And we call that acceleration normal acceleration. A2, which is on Valle, A1, which is on Sergio. Actually, if we cut or we let the rope loose, they will go on running in a direction which is tangent to the trajectory on each point. Let's see the same image from a different angle. As we can see now, Sergio is facing us, whereas Valle is facing towards the other side of the image. We can see the rope, and we can see how the tight rope is pulling Sergio towards right and is pulling Valle towards left. In both cases, towards the center of the circumference. In science, one of the meanings of normal is perpendicular, and that is why we call that acceleration normal acceleration, AN. The normal acceleration is always towards the center of the curve that the moving body is tracing. When we measure and we analyze the values of the normal acceleration, we find that it equals the square of the speed divided by the radius. That means that for a given radius, if the body is moving at a faster pace, it needs a higher normal acceleration. And for any given speed, if we are moving along a smaller circumference, the normal acceleration needs to be higher as well. We have studied that speed equals angular speed times the radius. So we can replace v by its equivalent, omega times rho, in brackets squared. We solve the brackets and we have omega squared times radius squared divided by the radius again. We can compensate, we can cross over the squared and the radius in the denominator, and we obtain that the normal acceleration equals the angular speed squared times the radius. Therefore, for a given circumference, higher angular speed implies higher value of the normal acceleration, or for any angular speed, a higher radius implies a higher value of the normal acceleration. Now let's consider what happens when we are moving along a straight line. Straight line is defined in mathematics as a circumference whose radius is infinite. Let's replace in the expression. If the radius is infinite, when we make the calculation of the square of the speed divided by the radius, it equals the square of the speed divided by infinite. But any number divided by infinite equals 0. So the normal acceleration is 0. Straight motions do not have normal acceleration. But, and here comes the important part, if rectilinear motions do not have normal acceleration, when a movement is not rectilinear in any shape or manner, it does have a normal acceleration. Therefore, all non-rectilinear motions do have an acceleration. And you will say, what then about the uniform circular motion? Well, actually, that is not an extremely correct name. We should call it circular motion with constant angular speed. But we use UCM as a way to simplify. It is important, though, to bear in mind that all non-rectilinear motions do have an acceleration, as we just said. Let's solve a numerical example of what we just said. Let's find the accelerations for the two children in example 1e. On the merry-go-round, one at 4 meters from the center, radius 1 equals 4. The other one at 3 meters from the center, radius 2 equals 3 meters. And with a constant and common angular speed of pi divided by 6 radians per second. First of all, as always, we will draw a scheme. We have A1, acceleration 1, acting upon child 1, and A2, acceleration 2, acting upon child 2. We know that the normal acceleration equals the square of the angular speed times the radius. Therefore, for child 1, AN1, normal acceleration 1, will be angular speed 1 squared times radius 1, and as the angular speed is constant and common, we can write pi divided by 6 squared, which is the common angular speed, times 4, which is radius 1. If we solve the brackets, it is 4 times pi squared divided by 36, 6 squared. And that is pi squared divided by 9 meters per second squared. Pi squared is roughly 10, roughly equals 10. 10 divided by 9 is 1.1, 1.1 meters per second squared for the first child. For the second child, AN2, the normal acceleration for child 2 will be angular speed 2 squared times radius 2. But again, the angular speed is the same because it is common. Then it will be pi divided by 6 in brackets squared times 3, which is 3 times pi squared divided by 36. 3 divided by 36 is 1 divided by 12. So it is pi squared divided by 12 meters per second squared, which is approximately 0.8 meters per second squared. Common angular speed, lower or shorter radius for child 2, and therefore lower normal acceleration for child 2. Obviously, as they move along the circumference, and as we saw in the animation, with a lower radius with the same angular speed, the linear speed needs to be smaller for the inner child. Let's now proceed to analyze cogwheels. We have two cogwheels in the image. For the cogwheels to be able to function properly, the cogs, the teeth, need to have the same size, otherwise they cannot fit in each other. But we know, and we can see in the image, that the number of cogs is proportional to the radius. That is the meaning of that sign, which looks a little bit like Greek alpha, or like the infinite without the last bit of the second circle, the second loop. The number of cogs is proportional to the radius. Then, at the same time, the brims, the perimeters, need to have each of the points the same speed, so that the cogs are inserted in each other in an alternation. Therefore, As we know that the speed equals the angular speed times the radius, we can say that for the first cogwheel, angular speed 1 times radius 1, which is the speed of a point on the brim, equals for the second cogwheel angular speed 2 times radius 2. And if we find out angular speed 1, it will be angular speed 2 times radius 2 divided by radius 1, meaning the angular speed is inversely proportional to the radius. You have a larger radius 1, the angular speed for cogwheel 1 is lower. You have a shorter radius 1, the angular speed for cogwheel 1 will be higher. And that is how we can transform the angular speeds with different sizes of cogwheels. To illustrate what we just saw, let's solve a numerical example. A cogwheel whose radius is ρ1 10 centimeters is connected to another one whose radius is ρ2 equal 5 centimeters. If the first one moves at a rotation rate of angular speed 1, omega 1, 20 rotations per minute, find omega 2, angular speed 2. First thing we must ask ourselves is, which one rotates faster? As we know, for the cogwheels to work, at the brim, the cogs need to move at the same pace. But the linear speed, the speed of the brim, equals the angular speed times the radius. If they need to be the same, therefore, omega 1 ρ1 equals omega 2 ρ2. And we need to find omega 2, angular speed of the second cogwheel. We need to clear omega 2 from that expression, so we take the second half of the equation and we divide it by radius 2. Omega 2 radius 2 divided by radius 2. We cross over radius 2 and we obtain omega 2. And that equals the first member of the equation divided again by radius 2. Omega 1 radius 1 divided by radius 2, which is omega 1 angular speed of cogwheel 1 times radius 1 divided by radius 2, which is 20 rotations per minute times 10 radius 1 divided by 5 radius 2, and that is 40 rotations per minute. That is all for today. In sciences, as in life, as always, enjoy.